Hello, students. Let me ask you something. Have you ever wondered how banks process hundreds of financial entries or how GPS systems calculate your exact position on Earth? Behind many of these real life solutions lies a concept called systems of linear equations. These systems involve multiple equations with variables like x, y, and z, which we want to solve all at once. But doing it manually can be tedious. That's where matrices and determinants step in. They allow us to represent and solve these systems efficiently by converting them into matrix form. Now let's understand how we classify systems of equations. We call a system consistent when it has one or more solutions. It is inconsistent if no solution exists. To test this, we compute the determinant of matrix A, which is mod A. Case 1, if mod A is not equal to 0, the matrix is non-singular and the system has a unique solution. Case 2, if mod A equals 0, but the adjoint of A multiplied with B is not equal to the 0 matrix, then the system is inconsistent. Case 3, if both mod A equals 0 and adjacent A times B equals 0 matrix, the system may have infinitely many solutions or sometimes none. It depends. So yes, checking the determinant tells us a lot before we even attempt to solve anything. Here comes the core method, solving using matrix inverses. Suppose we are given a system like a1 into x plus a2 into y plus a3 into z equals d1 and so on. We write it as a matrix equation A x equals b. Now, if mod A is not equal to 0, we find the inverse of matrix A, that is A inverse. We then multiply both sides of the equation by A inverse, giving us A inverse into A into x equals A inverse into b. Because A inverse into A equals the identity matrix, we are left with x equals A inverse into b. This final expression gives us the unique solution to the system. So instead of juggling equations, we've boiled the problem down to matrix multiplication, a massive win for clarity and speed. Let's see how this works with a two-variable example. We are given 2x plus 5y equals 1, 3x plus 2y equals 7. First, write the coefficient matrix A as 2, 5, 3, 2. Then mod A equals 2 into 2 minus 3 into 5, which is 4 minus 15 equals minus 11. Now let's find A inverse. The adjoint of A is 2, negative 5, negative 3, 2. So A inverse equals 1 by negative 11 times this adjoint matrix. Then we multiply A inverse by matrix B, which is 1 and 7. The product gives us x equals 3, y equals negative 1. And that's our solution, clean, fast, and exact. Now for a more complex example with three variables. We are given 3x minus 2y plus 3z equals 8. 2x plus y minus z equals 1. 4x minus 3y plus 2z equals 4. We write A as a 3 by 3 matrix with these coefficients and calculate its determinant. Let's say it comes out to minus 17, so it's non-singular. Next, we compute the adjoint and then A inverse by dividing the adjoint by minus 17. Finally, we multiply A inverse by B, which contains the constants 8, 1, and 4 to get the solution. After performing the multiplication, we find x equals 1, y equals 2, z equals 3, no messy substitution. Just matrix power. Let's try a word problem. The sum of three numbers is 6. If we multiply the third number by 3 and add the second, we get 11. And the first plus the third equals twice the second. Let's name the numbers x, y, and z. the equations become x plus y plus z equals 6, y plus 3z equals 11, x plus z equals to y, or rearranged as x plus y plus z equals 6, 0x plus y plus 3z equals 11, x minus 2y plus z equals 0. Now form matrix A using the coefficients matrix X with variables x, y, z and matrix B with 6, 11 and 0. Compute the inverse of A and multiply it with B. The final result, x equals 1, y equals 2, z equals 3, which checks out with all three conditions in the question. So, what did we really learn today? Determinants help us understand whether a system of equations has a unique solution, no solution, or infinitely many. By expressing equations in the form A x equals b and checking whether mod A is non-zero, we can solve them using matrix inverses. The method is compact, systematic, and incredibly useful whether in classrooms, computer algorithms, or engineering applications. And that's the foundation of how we solve systems using determinants and matrix methods. In the next video, we will explore how Cramer's rule gives us yet another powerful technique to solve linear systems. See you there!